said we normally have controlled and uncontrolled. Uh, Uncontrolled if it's where we are using diodes. Remember we said for diode is if it is forward bias, it will allow current to pass. If it is reverse bias, no current passes. The same with the diodes, sorry, with the resistors. But for the resistors, even if it is forward bias, we saw that we need to give or to inject some currents at the gate for it to ignite or for it to start conducting. So we have the ability for the resistors to decide after what time, at what interval can we inject this current, and that is what makes us to have controlled rectification and uncontrolled. So this is just a recap of what we saw during our the last class we had, where we had this kind of circuit. This is the source, and this symbol shows that it is alternating current, positive and negative. So we have a positive cycle and a negative cycle. So when we only have one diode, we only allow positive cycle to pass. So it is only forward bias to the positive cycle, but it is reverse bias to the negative cycle. So for the input that we are giving is sinusoidal. This is the input power here, the sinusoidal that from the source that we are getting. But now the diode only allows the positive part to pass, and it is a reverse bias to the negative cycle, and so it blocks the negative cycle, and so on. All the positive cycle will be allowed to pass through the diode, but all the negative cycle will be blocked because of reverse bias connection. So this is an uncontrolled kind of circuit with or we can say it is a half-wave rectifier circuit with the load being only resistive. So for a resistive load, you'll find that the curve for voltage and that of current is similar. The only difference is that the amplitude, since we normally get the current as a result of dividing voltage with a resistance. So the rest is the same. So yeah, that is a half-wave rectification using a diode or uncontrolled kind half-wave rectification. And then I said you can draw when you have another diode now which is forward bias to negative uh, cycle, and you get to see what happens there. So from the calculation, we're able to see that the power that we normally have, the voltage is equals to, or the source voltage is equals to root mean square or root 2 Vp, the highest point of the amplitude of the sinusoidal wave, multiplied by the sine of the curve, or the point is that whatever we are having here is sinusoidal, and so that is the equation. So mostly in Kenya, this Vp is normally the 240. When we say single phase is 240, that is the Vp. So you can be able to substitute a Vp and maybe calculate. So for this equation is that we are injecting a full cycle 2 pi, 1 over 2 pi, or up to 2 pi, but the result is between 0 and pi. The output is between 0 and pi, so that sets the limits of the output voltage. This voltage is what we are substituting with this that you are given here, and we did that, and we were able to find the results to be root 2 Vp over pi. So during your calculation or during exam or cut, you are supposed to show the working here. Like when you integrate, you remove the two constants outside the integration, and then because if you integrate a constant remains to be constant, but now you integrate the sign, which you saw when you integrate sine omega t, you find negative cos omega t, and then you substitute with these limits, the results will be root 2 Vp over pi. So that is purely resistive load with a diode. Then we can see the same circuit now with a thyristor. But as I said, with now the thyristor, we can decide at what point are we igniting. With diodes, we don't have the ability to control that. So for diode, it starts from 0. That's why the limit for diode is 0 to pi, but for the limit for thyristor now it will be between pi to alpha. So the same, the thyristor is only forward biased to the positive half cycle of the curve. So it will only allow that half cycle to pass, and only also we are not igniting the whole of the curve, we are only injecting at a certain angle. And this angle can vary. You may also want to ignite it at 0, so your angle will be, your alpha here will be 0. You can ignite it at 60 degrees, at 90, at 120, all the way to close to pi, and continues. But now the thyristor is reversed bias to the negative cycle, so it will block the negative cycle. Again, we go back to the positive cycle, which it will be ignited at 2 pi plus alpha, or after an angle alpha, and so it will conduct that positive cycle. So it's similar, the only difference is that we are able to ignite or to control at what point do we want to ignite it. Yeah, so if you were to substitute that, the equation remains the same, but now the limit is alpha to pi, and so the equation now for the other one, we had cos 0 at the other side. Now this is cos alpha. So the other one we were able to remain with 2 here, which were cancelled with these two, but now here we have a known, the angle alpha for the thyristor. So you can see, so imagine you have a machine, and maybe the kind of control you only, let's assume you are able to control with one diode, is a DC machine, and now you have been able to rectify the sinusoidal wave. When we say this is alternating current or AC, because we have both positive and negative, but when you use one diode, you're able only to have one positive. So it is one unidirectional, or we can call it is a DC, but not pure DC, because pure DC we know it should be a straight line, but we are almost achieving that because now we're only having the positive. So imagine you have a machine, so you switch it on, then at a certain point it goes off, then switches on again. You can imagine the efficiency all the time, it will take longer time, and so on. So that is the diode and the thyristor with the purely resistive load. But now when we are dealing with motors, so not that a question can come that, or as I said, you draw, you're told to draw a circuit of a half-wave rectifier using a diode, show the waveforms, and derive the equation of the output voltage. So that one, you are expected to draw this kind of circuit and these waveforms of the input and the output voltage, and also current. Specifically showing this for the thyristor, you have to show the alpha angle. If it is one thyristor, show this gap, like the waveform should flow. Like this is pi, then the next one is pi, like it should be in one graph kinda, where you are putting these two, the input voltage and the output voltage. Yeah, so for when we talk about motors, they are normally have kind of a reactive load. We have both inductance because of the coil, and also resistance. So what happens to their kind of voltage output, or the output, when you have both? So I don't know. We are going to, yeah, full wave converter. But before we go to full wave converter, we have this kind of situation where we have a load, which is a motor, which I said for a motor it's a reactive load. We have both inductance and resistive or resistance within the motor. So for this case, if you remember when you were talking the theory within the theory of thyristors, we saw that the moment you have inductance, we are able to make current lag or take more time to pass through a certain circuit for a longer time. We're able to increase the time limit that a certain amount of current passes through a circuit. Maybe it was taking 2 seconds. Now, when we have inductance, it makes it to prolong or to take more time, maybe to 10 seconds. So you will find that, for instance, this is the input voltage, but because the load is have an inductance in it, then the current will not settle or will not go off the same at pi. Remember, for the first one, it was going off at pi, or it was reducing to zero at pi, but now it takes more time and falls uh, to zero at beta. But again, now the voltage will not fall to zero at voltage will fall to zero at pi, but we need a certain current to drive this current, a certain force potential, like voltage is the one that makes a current to flow through a given circuit, or is the force behind electrons moving in a circuit. So this part of current will be driven within the circuit by the some part of the negative cycle. But this only happens because we have inductance in place. So the whatever we had will be distorted, the current one, but the voltage now we have also some part of the negative cycle coming in to drive the this current that we have lagging because of inductance. So we this is still a single thyristor, which is only forward biased to the positive voltage, but because of inductance in the circuit, we have current lagging going beyond pi, and so it needs certain voltage. And a certain negative voltage will be allowed to pass through the thyristor to be able to carry the current within the system and so on. So the other part of the negative cycle is blocked by the thyristor, and then again we go to the other positive cycle, which is ignited at pi, and the voltage falls at 3 pi, but has to we have to use some of it negative part to allow this current that has extended or have lagged to settle to zero at 2 pi plus beta. So that is the whatever the what whenever we have an inductive load. So you can also compare, like you can be told to compare or give the waveforms diagram for a purely resistive load and another one that is reactive. So this is what will be different from what we had here. So we have current settling at beta. For this current will be have settled at pi, but for the other one is prolonging or lagging and settles or goes off or commutates at an angle beta, which is greater than 180 now. Yeah, so that is a single thyristor with an inductive load in place. And mostly when we only have one, we're only converting one cycle, positive or negative. We can either convert, maybe this thyristor could have been made to be forward bias to the negative. Now we'll be converting these negatives will be the one which will be here on this side or on the other side, depending on how you have done connection, but mostly on this side, sorry, on this upper side. So for this kind of circuit, we said we call them half wave rectifiers, and so we also, to improve efficiency, we need to convert both cycles so that we can ensure there is continuity of power. So we also have the full wave converters, which can either use fully, we can have some that are fully using diodes, but for real-time application, we normally have them, we normally use thyristors, but we can also combine thyristors and diodes. So for this, we'll be able to convert both the positive and the negative cycle. So you will get to see that S1 and S2, thyristor S1, S1 and S2 are forward biased to the positive cycle. So they allow, or the forward bias cycle is the positive cycle is forward biased to The thyristors are forward biased to the positive cycle, S1 and S2. So they will allow that to pass through, and then they will block the negative cycle. But the negative cycle now again will be allowed to flow through S3, S3 and back through S4. So S3 and S4 now will be conducting the negative half cycle, and as a result we are able to allow both the positive and the negative to pass through the thyristors and to reach the rod or the machine that you have attached there. But this is purely resistive. This is purely resistive load, so you can see the current and the voltage are settling at the same time at pi. But the point is that now we are able to convert both the negative and the positive half cycle, and so the frequency or the the frequency of the output has increased by 2. So the first one, the frequency, this sinusoidal, this is the frequency of the curve. The first one, we can say this was the frequency. Yeah, this 0, the negative cycle was not being rectified, but now we have increased the rectification by 2, and so we can say for a single thyristor rectifier or a half wave rectifier, we can say frequency is F1, but for a full wave, now it will be twice the frequency of a half wave rectifier that we had previously. So we are able to increase the rectification by using a full wave converter. Again, for the full wave converter, for the sake of, for instance, in situation where we have motors, we said the presence of inductive coils will make the current to lag. And so you can say somehow presence of an inductive load ensures that we have more continuous current within the system, which is what we really want to achieve, a straight line. So an inductive also coil can help us with that because of ensuring that there is a lagging current within the system. So for when we ignite at an angle less than 45 or less than 90, we get to see that this angle, the igniting angle, is less than 90. 90 is at the middle of the one of the half curve cycle. And when we ignite it at an angle less than 90, we are able to feed power to, or to give power to the whatever machine that was attached here. So this is from the equation from is the equation of this full wave converter. I think the equation will come later. So this being the equation, if you substitute to an angle that is less than 90, you're able to find a positive value, which means that we are able to feed power to the machines that is attached there. But if you ignite it, if you ignite it at an angle less than 90, but if you ignite it at an angle greater than 90, remember the curve was full here. So if you ignite it at an angle greater than 90, the end result of this equation will be a negative a value, which means now the machine is acting as a generator. Remember when you are doing your electrical machines, you're able to find is the same machine. It can act as a motor and as a generator at the same time. If you feed electrical power to the stator and you're able to have the shaft rotating, then you can tap the mechanical energy from the shaft. The other way around, you can start by rotating the shaft using maybe wind energy, hydro energy, or whatever is turning turbines, the shaft. And from the other end, from the stator cables, you can be able to tap electrical energy. So the same for this, depending on the ignition angle, you can either have power being received by it becomes a motor. You're able to feed power and you're able to harness the mechanical energy. But again, if you ignite at an angle greater than 135, you are able to generate power from it. So this is the whatever, like, and we also say whenever it's generating is more of inversion, we say it has been inverted. It's no longer rectification, but below 90 we say is rectification. So again, we can say for the inversion, this is normally used for regenerative braking. I think you covered that. Is that? Yeah, it's normally used for regenerative braking of a motor, and it's normally called as an inversion operation. So we can also have thyristors or full converter, two of them. One you ignite at an angle less than 90 and another one at an angle greater than 90. And we call that kind of a converter a dual converter to achieve those two characteristics at the same time. But maybe you will not switch them at the same time. But when you want to have the regenerative braking or braking the motor, now you ignite the other converter and you shut the other converter and you have the reversal of the operation of the system. Yeah, so we have all those, and you can be given an equation. Mostly is this one. The main equation is this. Know how to write the equation and how to integrate and substitute the values, and mostly you'll be given the value of alpha and the value of this voltage, and now you can be able to find the final result. So there are those examples that system, and we normally call that semi-converter. The thyristor semi-converter, meaning now we have two what? Two thyristors in place and then two diodes for the feedback part of the system. So for the first cycle, we have S1 and D2 and forward bias to the positive voltage, and then S2 and D1 are forward bias to the negative voltage. But again, before we ignite the second thyristor, we now bring a diode that is called a freewheeling diode that we allow to carry the current before we ignite the second thyristor. Remember, when we have a machine which is inductive, we have some current that will be dragged and it will take more time. So we allow that current that is dragging before we ignite the other two pairs to pass through the freewheeling diode, yeah, before the other one is ignited. So you will see when S1 and there is a 1 and diode 2 are conducting, the current passes through them. Then when they the positive voltage goes to zero, the current that was lagging behind, or that was made to lag because of inductive load, it is carried through freewheeling diode, and then the other thyristor is ignited, or S2 is ignited at pi plus alpha, which now the S2 and D1 start conducting the current. Then before we go to the positive half cycle again and ignite S1 and D2, we have freewheeling diode coming in. So that is how the freewheeling diode is used. And now you can see we don't have the negative voltage having to carry the, or to push the current that was lagging, because we have already taken care of it through the freewheeling diode. So we are still able to attain almost a straight line through that. And the voltage, output voltage also, we have both the negative and the positive cycle forward bias through connection of both the resistors and what, diode. So the equation now, the limits, we are able to give a 1/2 cycle of the system, and we are able to get output of all. No cycle is being blocked. So the limit, or the outer bracket, will have 1 over pi integration between what is the output alpha to pi. What is the output? The limits of the output is alpha to pi, and then root 2 Vp sine omega t. Then you do substitute or remove the constants and integrate sine omega t. You have 1 plus cos alpha. So again, you can be given the values of voltage and alpha, and you are able to work on the, or find the real values without unknowns within the system. So we have a lot of theory in between. Maybe you can check it on your own time to understand it. But mostly that is the working principle of this rectifier converter. So you have to understand the forward bias and reverse bias kind of junction to know why are we only allowing the one part of the cycle, then be able to derive the equation and draw the waveforms, and you'll be good. But make sure you understand that 1 over diode, a single diode, and a single thyristor, then it will be easy to also understand where we have full converters and semi-converter, and what happens if we have, or what is the difference between a poorly resistive load and what, a full with a reactive load where we have inductance in place. So a quick one, maybe on your calculator, you can try to substitute in this equation. Where is that equation? If you are told that Vp is 240, what will be your output voltage for this situation? If you are given your output voltage to be 240, what will be the output value? Maybe you can type on the chat. What are you getting if you are given yeah, thank you, Christopher. That is 108.03. Then for this is a single for a diode. Here is only a diode. Then we go and see that of a thyristor. So we get to say, if we ignite the thyristor at 0, we get to see is the same, behaves the same as uh, a, uh, a diode. So for this instance now, this is for that of a thyristor. So let's ignite it at 0. So you start and find the, and also Vp to remain as 240. So you find cos 0. You substitute cos 0 and see what it gives. You can do it with your calculator. Now you're assuming that our alpha is 0, or we ignited the thyristor at 0. What will be the output voltage? Christopher, redo again. Cos alpha now cos. Now we have alpha 0. 191. Why are you guys getting 191? It is not 191. VP is 240. Yeah, it's still the same as the first one. It's still, Peter Chege, thank you. It's still 108. The moment you ignite the thyristor at 0, it will give you the same result as that of a diode. So maybe we'll check where you made a mistake. Then we can say, let us ignite it at 60. Let alpha be 60 and ignite the thyristor. What will be the value of the voltage? Yeah, I think it's 81 point. Da, da, da. Yeah. So mostly you can be given a situation of maybe you have two thyristors or this is a single thyristor. You draw a circuit waveforms, derive the equation, and then you are given values to substitute. Maybe you find the voltage and also current. So for this instance that I have just said here, here we have alpha as 60. If you are told that um, resistance, this is purely resistive. If you are given that told that resistance is 10 ohms, what will be the current? Yeah, what will be the current and what will also be the power? So if you are given the resistance as 10 ohms, what will be the current? The next one, power. No, Moses, current is not 24. I don't know what you used, but current is not 24. So for Alvin, we have that equation on that equation 10.2 on the screen is what we are trying. We started with substituting alpha. We took alpha to be 60 and VP to be 240, and we're able to find voltage as 81.02. So now we are finding current given a situation that resistance is 10 ohms. And Christopher has said that current, which is true, will be 8.1, where we current or we normally get current as voltage divided by current is voltage divided by resistance. That gives us current. And then I asked about where are we? I'm lost. Where are we? Yeah, this equation. And then after current, I also asked about the power. Resistance will be 10 ohms. Yeah, so for power it will be voltage 65. Yeah. Is it nani amesema kilowatt? Oh, okay, let me do and see. 81. What was the voltage? $81. It will be 656. Let me see. Yeah, it should be 256 point something, which is watts. Sorry, watts. I don't know, Christopher. Your kilowatt is not okay. If you are to convert this to kilowatt, it will be 0.656. You divide by 1,000, and you get 0.656 kilowatts, or you read it as 656.62 watts. So mostly that is what mostly you have to do with this kind of equation. You're able to get to see if it is a motor, how much voltage is it getting, current, and power. We can also find power, but mostly again maybe this is just maybe simple calculation basic. But for a motor we normally also include the cos power factor, which we get to see whether is it this alpha or we have a different kind of power factor within the system to be able to really get the amount of power that gets to that machine, and also get to understand this kind of waveforms and the circuit. You can either be given the circuit or you are required to through the circuit. You ought to also understand how to go about it. So we are able to cover the thyristors, the rectifier or the AC to DC converter using diodes and the thyristor, and a single phase. We only have only one circuit, only one source, so a kind of a single phase input. But we also normally have three-phase inputs, which we not cover. We just first understand the single phase system and appreciate them. The moment you understand the single phase system, for three-phase system, it's easy because there is more of these single phases that are put together, three of them, but now they do not start at the same time. We normally say they are uh, electrically displaced by 120 degrees. So the first one, if it is at 0 degrees, the other one will be after 120 degrees, and the other one will be before at one negative 120 degrees, so they are displaced by 120. So we have this one, this other one, and this one to make a three face. But for this unit we will not be covering those. I will try to uh, for this book, this is a book I took this chapter, so I will also try to remove this part that will not be covering. So in our next class we'll be going to the next converter, that are AC converters, AC voltage controllers, and it is very short because we also be covering the single phase only. So in our next class we'll be able to cover the rest of the converters. Then the other class will be able to go to the mechatronics part, which is also not very detailed. But before then, I will also send a cut. I've been sorry. Were we using V not as resistance? No, sorry. The resistance I gave it as 10 ohms. I had given resistance as 10 ohms. Okay. Yeah. So before we go through that, I have also prepared a take a recut which I will share to your class rep, and also you submit it through Google Form, and deadline is on Tuesday next week. Yeah. So maybe we'll cover, and then after covering, then the whatever. So the next 2 weeks, the other week, we may have a physical, as we also do a cut too after we are done with the syllabus. So unless there is a concern or a question, we are done with today's class. Karibu Moses.